Okay, today we're going to be looking at breakdown voltage and lightning. So, previously we're going to be thinking about insulators, and we were looking at last time the energy bands of an insulator, and we remember we have our filled band, we have our valence band, and then we have the conduction band away up here. I'm not giving myself much room for this. And here we have the band gap. Now, we know for insulators, the valence band, although it's not full for most insulators, the element will bond with other atoms in order to get a full outer shell and to fulfill this valence band. And that means that for insulators, this atom is not going to readily give up its electrons to be used for conduction. However, there are no perfect insulators. So if an atom is given enough energy, electrons can escape to the conduction band. And when that happens, we can then force an insulator to conduct electricity. The point an insulator starts to conduct is the breakdown voltage. So if we think about when a very large potential difference is applied to a conductor, the electrons have enough energy to break free. Now this can pose a problem for engineers. So when an engineer is designing a product, they need to take into account the breakdown voltage of the material that they're using. However, this isn't as easy as what as it sounds. So the breakdown voltage can change with tiny differences in a material. So instead of defining the exact number at which a breakdown will occur, manufacturers will rate the maximum voltage where an insulator is safe. Now, if you look in the higher physics, Hodder Higher Physics textbook, they give you a nice picture of a dielectric breakdown within a block of plexiglass. And if you look at it, it looks like something very familiar. It looks like lightning. And that leads us to the natural occurrence of electrical breakdown. So lightning is a natural occurrence of electrical breakdown. So imagine we've got a cloud here and you've got static build-up. And here's the ground down here. You've got a potential difference here. Now air is an insulator. But when the voltage in the static build-up becomes so high, we will see lightning. So, potential difference. When the electrostatic build-up occurs, the potential difference becomes so great it can cause the electrons in the air to break free. So the current in lightning is anything between 5 kiloamps to 20 kiloamps, so really quite significant, but it's been recorded at 200 kiloamps. Now, this can lead to some really interesting effects. So let's say this is sand. This is not just the ground. This is sand. Sand is a silica. And this causes lightning can heat the sand and melt it, creating really interesting things called fulgurites. Now these are hollow tubes of basically like glass, because sand is what we make glass from. So you get these hollow tubes that look a bit, they're like glass, and they look a bit like roots of trees, and they basically leave like an imprint of the lightning on the sand, and they're really quite cool. You can Google images of them. Now what about thunder? What is thunder? The sound, what makes the thunder? So what happens is the air, as the lightning travels through it, gets superheated. And so as it gets superheated, there's a rapid expansion which creates the boom of the thunder. And if you've noticed, and if you think about on a really hot, muggy day, and you just feel there's going to be a thunderstorm in the summer, and everyone says, oh, we need a good shower of rain, or we need a good thunderstorm to clear the air. After that thunderstorm, you have that clearing of the air. What's happened is the lightning has caused an ionization of the air, and that's what clears the air, because that air, that moisture-rich air before a thunderstorm is full of water ions, it's full of ionized particles, free radicals, and these get cleared out by the lightning. And so that's why the air is much cleaner feeling and fresher after a good lightning storm. However, interestingly, we know all this stuff that we know about lightning, we still don't fully understand what causes lightning, and there's still more to learn, which I find really interesting.